So let's start. My name is Szymon Kulec. I'm the lead developer advocate at RavenDB. And the main topic of this session is it's still C#, and the subtitle is Practical Systems Programming with .NET. So I need to mention that I'm .NET Framework 1.0 old. That means that back in the day, my most favorite type was array list. Never used that. It boxes all the time. Back in the day, structs was the thing, actually, with the 1.0. And back in the day, we had this joke that it's awesome because it's not Java. Nowadays, we don't use that joke, but I need to mention that version 1.0 of .NET Framework, there were no generics, no ref structs, forget function pointers, and don't even mention span. Now, I need to also mention that there is this objective distribution of human perception. If you take a look at the left, like the middle should be pretty good. It should be Gaussian. Western Europeans are similar, and there is the bucket where I put myself. I'm from Poland. So Eastern Europeans say if something is less than 70%, basically what is this garbage? So this is just to set the expectations for these, for the talk and whatever I share during this talk. I need to ask, .NET anyone? Awesome, I'm in the right room. Benchmark.NET anyone? A few hands doing micro benchmarking, awesome. And the last but not least, have you ever built a custom vectorized implementation of constant similarity so that even without IVX 512 enabled, it properly unrolls vector 512 to two separate lanes of vector 256 operations? A few hands, okay, so you will learn nothing, but the rest maybe you will. So let's start with this beauty, and it's called interfaces with static virtual numbers. Virtual members, not numbers. So as you can see here, we have two, like the pretty basic types, int and double, and they both currently implement like 100,000 interfaces. Like the list is infinite. But one of them is iNumber based, and this is quite an interesting one, because if you take a look at it, and you can see it at line 5 to 9, basically what it does, first it uses this beautiful hack that tself implements the interface. The reason for that is that if you take a look below, you'll notice that there is this static abstract tself1. What it means? It means that if we follow this beautiful semantic structure, or syntactic structure, you will notice that every single type also implements this property, which allows us to perform quite an interesting thing, which is you can define 1 for integer, you can define 1 for the double as well. Now you may say, okay, we just define a static property over an interface, and every single class or struct that implements that needs to provide that as well. So let's take the following thing. This is a small snippet of a benchmark. Benchmark.NET, already mentioned at the beginning, is a tool for micro-benchmarking your code. So if you want to prove that you are faster than the rest of the folks, that's the tool that you want to use. At the top, you can see that we use memory diagnoser because fast folks in .NET do not allocate at all. So we want to see zeros there. And then there is the disassembly diagnoser, which will allow us to take a look at the assembly, like the raw machine code that is eventually is the eventual outcome of this whole compilation and running. As you can see, there is this small method add1, and this method, it shows you this beauty that with this with these static virtual members, you can right now write, for example, an extension method that will take that into consideration. And now we have two benchmarks. One benchmark is run for the integer, and the second is run for the float. Again, we are just adding 1 to 3 or 3 in the float space. So if we run it, you will notice that this is pretty fast. So first, please notice the second column from the left, meaning the mean time of running this method. It runs under 100th of the nanosecond, which is ridiculous because it's less than the actual error of this measurement. So something is fishy. If you take a look at the last but one column, you will notice that the code size for this method is 6 bytes. It's unreasonable, and it cannot be true. And if we take a look deeper, we will notice that the JIT compiler, so basically whenever you compile C#, C# is compiled to the intermediate code, and later when you run it, the JIT compiler, just-in-time compiler of .NET, will spit out the beautiful assembly. And as you can see, everything has been inlined for us. There is no method at all, and this benchmark just returns 4 for the upper part, which is the integer, or it loads something, some magic into the registry and returns the same for the float. So we just got a pure performance, everything is inlined, all the methods are removed, and this is partially the beauty of these static virtual members, especially if you take into consideration that JIT loves it, especially if you use it with structs, because then, if you are familiar with .NET, probably you know that if you have a generic parameter, and this parameter is a struct, JIT will emit a special customized method for this structure. In my opinion, your expressiveness with code goes through the roof. Like if you have, even if you have like a fancy business domain, having this ability to add the static property on the interface can enhance your like whole modeling area, because then you can build an extension method on top of that and push it even further. The last but not least, we observed tremendous performance gains. There are some disadvantages. All tricks, like if you are familiar, there was this trick with default of t-struct is no longer needed. And there is the other disadvantage, it's new C#, so I need to learn. Terrible, terrible stuff. The second part is taming the state machine. So in .NET we have this beautiful, and in C#, sorry, we have these beautiful two words, keywords, async and await. And there is this notion of having a method and labeling it either as a blue method or a red method. A blue method is a simple synchronous method. You just call it and it returns. Then there is this red method which includes all this async machinery, which means that you can call a blue method from the red method, because like the async stuff can call synchronous stuff, but you should not call the red method from the blue method. If you do, don't call me. Then we have the purple method. If I do my color math correctly and you combine blue and red, it should be purple. I'm not good with it, but please bear with me. So how could it look like this purple method? So we want to combine two words. We want to combine the words where this execution is sometimes synchronous, and on the other hand, we want to combine it with the occasionally asynchronous execution. The types are removed for now, but it should be something like this. We check if execution is synchronous, then we perform something, and then in the asynchronous path, we will try to await. Please keep this abstraction in your head for a second, and take a look at that beauty. So first, please notice the value task. Anyone use value task here? Okay, a few hands in the air. For those who are not familiar with it or never used it, value task is a awaitable type. You can await on it, but it's a struct and it allows you to wrap synchronously executed results in the same structure. And we do it in the very same way. So in line 6, you can see we have this check if completed successfully. And then if we know that this value task is completed successfully, we can just return this this result wrapped with the execution of do something. Now we also use this beauty of C#, where you can define a static method inside of the other method, and we can follow this slow path that requires async await and just return it as well, because it will be wrapped again by the value task. So we just combined two beautiful parts, the blue, synchronous execution, and the red, which is asynchronous execution. Now, if we take a look and we want to benchmark it again, we will probably use benchmark.net. As you can see, I sprinkled this get method with no inlining attribute, which basically says the just-in-time compiler, please do not inline it, do not optimize it. And if we run such a benchmark, you will notice a terribly skewed number. Probably it's totally wrong, because this task await stuff should take a bit less. There is like the initialization and all that stuff. But what I'm trying to show you is that for the synchronous execution, this value task purple function, let's go back here for a second, meaning that we follow this value task is completed successfully, etc., should be much faster. And if you notice the code size, so again, the last but one code size column, you will notice that value task await is much, much smaller. Now again, we all code in C#, so we love assembly, right? That's what we do. So if we take a look at the assembly, I won't be reading line by line, but what I'm trying to notice is that at the very bottom you will find this beautiful return in assembly, which means that the whole synchronous part of this method was properly jitted into small chunk of synchronous execution. The rest of this async await machinery is left to this slow path that we just added. Again, advantages or use cases. Like if you have almost async or almost sync scenario, for example, RavenDB, a database written in C#, usually it has data in memory, but sometimes it needs to take a look and use I/O. So it wants to reach a disk, some disk, for example. So that would be the case. In majority of the cases, we are ready to serve the data from memory, so we use the synchronous path. But for the other cases, we will need to perform some I/O. So that will be the second part of this execution. And advantage is that, as you can see, it's supported by the language like async await and the runtime. We have the value task that we can leverage. Disadvantages, a bit longer. The second is that it's a proven solution to this sync async, so we can't reinvent the wheel. It's terrible, and it works. So yeah, no blaming possible. Poor me. The third part is vectorize everything. This is quite a piece of code, and we won't be discussing it line by line, almost. And this snippet of code calculates XX#64. So XX#64, and this is snippet taken directly from RavenDB that I optimized like 6 months ago. So XX# is a non-cryptographic hash, which means that it's fast to calculate, but again, you can't use it for cryptographic purposes. So you can't sign a document with it or do like anything meaningful besides detecting that, oh, maybe something changed. Or sorry, yeah, like detecting the changes. So if we take a look at that, first we'll notice that we are setting some limit, then we are setting some for ulongs, which means that this hash operates on 32 bytes, that computes 32 bytes and moves to the next 32 bytes, and then moves to the next 32 bytes until it hashes everything. We have some operations here, like we multiply, add, and rotate. That's what you do with cryptography, nothing fancy. You just shift bytes left and right and multiply. And then we do it until the loop is done. But now if you take a look, you will notice that V1 depends only on V1 plus some data. V2 depends only on V2 plus some data. V3 follows the same path. There are no cross dependencies between these. So if you take a look at that part, and if you take into consideration that we are multiplying by the same thing at the end, like there are two prime numbers here, what you can do is that you can extract it and turn it into a vectorized operation. When you think a short introduction to vectorized operations on your CPU is that you have multiple things that are totally independent, but you perform the same operation over each element of an array, let's say. So that's why we combine these four ulongs, and we are looping over them using vectorized API. And even though you may say, oh, it's not C#, I would say that it uses BCL classes in the C# language, and it allows you to write pretty powerful vectorized algorithm. Now, if you take a look at how vectors work underneath, you will notice that every single operation has two attributes. The second is method implementation, which says like inline this stuff. Again, we noticed inlining in the first benchmark, like basically assembly was merged together. And then there is this beautiful other attribute called intrinsic, which means that .NET Runtime has a specific piece of assembly that will inject in place instead of this method. Now, if we compare the results, before you can see that hashing with XX hash took 490 nanoseconds, and after it was only 292, which gives us like 25% gain, quite a lot. And again, if you have this no interdependency between data, you may consider or think that, oh, that's potentially vectorizable. Again, advantages. For compute-heavy scenario, this is awesome. You should have no data dependencies, because if there are like cross-lane operations, you pay some penalty. And C# plus JIT, come on, it's a match made in heaven. Disadvantages, it requires thinking. So you need to think about data, and you can't say it's impossible with C# anymore. So huge disadvantages here. And there are so many more stuff, like things like this in C# and DBCL. Like you can prefetch CPU cache from C# right now. This is awesome. And there are so many more operations. For example, this is our cosine similarity for vector search. As you can see, it's again sprinkled with this low-level SSE2 extension of your CPU. So we like really push it hard. The next part is the by reference. Anyone uses by ref? Like someone writes ref from time to time? Okay, a few hands in the air. Basically what C# got, I mean not lately, but to me it's still like new C#, is that if you define either the variable I or an array or a span, then what you can get is that you can get a reference. Think of it as a pointer. I didn't say it. You can't quote me. But think of it as a pointer. So we can grab a reference or a pointer to this I. And also you can do it for the array. So you can grab a reference to an element in an array. There are two methods to do it. And .NET team is working heavily so that we no longer need the second one. And the same with the span. Now we can have some fun with these references. By the way, if you use in .NET, this is a read-only reference as well. You pass by the reference, but this is the read-only reference. As we have references, suddenly we can check, is it null? It's fun, always. Like if you can dereference a null pointer, things will blow up. We can turn things which are read-only into not read-only. There is a method for it. As ref, and it will just make it writable. You can add references, so you can jump to another element, adding by one. And this is my favorite one. I stumbled upon it like 100 times already, and I always forget. What will this do? Please notice that next is a reference, and we are adding next to the next 2 in this unsafe add. If you take a look closer, you will notice that I forget putting ref in front of unsafe. So that means that instead of assigning a reference, I just updated the value. And that happened to me so many times when I wrote like serialization stuff, you know, fancy C#. Yes, this happens in real life, and you don't get a warning because it's valid C#. So if you think about these references, again, you may think of it as a managed pointer, but don't quote me, because .NET people will eat me if I use managed pointer for a reference. It's great for data-intensive parts, like databases as RavenDB. We have a lot of it. And there is like reference anything. You can grab a reference to basically anything. An item in an array, or a span, or a variable. It's everywhere. Disadvantages. It's getting optimized more by the .NET team, so you need less hacks, and you don't need pointers to be fast. So huge disadvantages, nope, we don't like it. Yeah, so the last part that I want to, or the last but one, part that I want to cover is the Blittable JSON. So in RavenDB basically ingests and returns JSON. But if you take, and we all do love JSON, there is this system text JSON, which is great. C# source code generators for system text JSON. Anyone used the C# code generators? Quite a lot of people, awesome. But there is this thing. So, if you want to access a property of any JSON object, you either need to deserialize it fully, or you need to traverse it, because there is like no structure. You need to find this property. There is also this thing that if you have documents or objects that are repetitive in its nature, like you have a collection, you will have names that are duplicated multiple times across the document. So the question that we came up with is like, hey, what can we do? And clearly the first part, which already provides a lot of benefits, is mapping the names. So instead of using the names, we introduced a simple dictionary. And this is done in one pass only, because if you receive JSON and you write it to disk, once you, for example, find the name that is, a property named name, you just memorize it, that you assign 0 to the name. Then you go with 1 for founded, 2 for active. And as you write the document, you just put numbers instead of names, and then you memorize what happened next. Then you need to, for the serialization purposes, to the left, I mean the small blob to the left, you need to memorize the type. So it would be either string, integer, we memorize true or false, object, array, etc. And now we are almost at the end of the document. So what we need to do, we just created this map of integer to property or property to integer. We need to add it to the end of the document. But now we just added some blob, and there is no table of any lookup that you can use for that. So at the end, what we do is we are sprinkling that and adding the footer. So whenever you want to access the property table, first you will look up at the end of the document, and you will notice the footer, and then you will traverse it further. The advantages of this Blittable JSON are pretty straightforward. Like, first, we have almost all of one, if it's cached, property access, which imagine again with RavenDB. This is a database, so sometimes you deploy an index in a database, right? That's what we do. Something is slow, so we deploy the index. And imagine if that was JSON or JSONB, whatever, you would need to reindex the whole document. With that approach, if it's stored this way, you don't have to, because you then directly can access the given property. Then this JSON is much, much smaller because of the dictionary compression. We get it for free. All the duplicated names are removed and replaced with numbers. I already covered the accepting new indexes at will, and underneath it uses also the RavenDB memory pooling, which basically allows us to, again, not allocate, because fast folks do not allocate. Disadvantages, I needed to put something here, so placeholder, and sobbing face, whatever. And yeah, so if the question is it still C#? Even considering my Eastern European bias, I think the answer is yes. And I hope you enjoyed it, and maybe you have some questions. And please use that for the feedback. That's what I was told to put it in my presentation.